Who of you did not attend the previous talk? Okay, I'm going to cover the basics again then. My name is Paul. I study physics. I'm in my master's semesters, something like that. And this is a topic I'm essentially just interested in. So I thought I'd tell you all a bit about how we can go to the stars with nuclear reactors, or just nuclear propulsion. First of all, we need to talk a bit about rockets, what they essentially do and what we want from them. Rockets are a thing that make you go faster. They don't bring you from one place to another like a car. They make you faster because in space you don't define a point by where you are, but how fast you are. An orbit around the Earth has a certain speed. If you want to go to Mars, you need to match your speed to the speed of Mars, and so on. So from a rocket engine, you generally want three things. First of all, of course, you want thrust. You want a lot of force. You want power, because you want to gain energy very quickly. And then you want efficiency. And thrust and power, you can just slap on more rocket motors, but efficiency is something you're pretty bound to by the type of motor you choose. Chemical rockets, and this power is measured in specific impulse, or ISP. It's a term of seconds. We don't really need to know what it means. We just need to have a feel of magnitude here. Chemical rockets can't break above 500 seconds ISP. That's just chemically not possible. I have a certain amount of energy per molecule I can use. ISP is essentially how fast stuff leaves the rocket. The faster I can throw things out, the more ISP I have. That's why ion engines are so efficient. I can throw them out a lot faster, so I can get to ISP of around 10,000. That's possible. They are actually so efficient that we're trying to dial down their efficiency to get a little bit more thrust, a little bit more force, because otherwise it would be pretty boring, and they would take even more time than they need now. If we use nuclear reactors as energy source, we can bring that up. Essentially, the more temperature we can reach, the higher the temperature in our rocket is, the faster things come out. So first of all, we need to decide for an energy source of our nuclear reaction. And let's try fusion first. Fusion is, from a nuclear standpoint, very simple. You take two things, you make them go very close together, and they will do a reaction, you get energy. That's simple. You look up in the sky and you see millions of fusion reactors all the time. They're called stars. The challenges to make something fuse is essentially to have something at extremely high temperatures, at a very high pressure, and to keep it that way. If you have such high temperatures, you have a plasma. If you have a plasma at such high temperatures, touch a wall, the heat flow through that single point is so big that essentially all your energy in the plasma is lost through that one point. Your wall is gone, it's vaporized or something, and your plasma breaks down, your fusion has stopped. That's what you're trying to mitigate. And just to give you a bit of a feel where we are here we have a measure of reactivity. Units are unimportant. Here are different types of fusion, and here is the temperature range where we are, billion Kelvin. That's so hot that the thing radiates in the hard X-ray spectrum. You get some UV radiation from the sun, and if you make that a lot hotter, you get to X-rays. That's where a normal fusion reactor works today. That's why it's very simple to observe your fusion reactor. You just need to look at it from any point, and there is enough X-ray coming through your fusion reactor to observe the plasma. What you also see here in the different fusion reactions, the deuterium-tritium reaction, that's hydrogen with 1 neutron plus hydrogen with 2 neutrons, that happens at a very moderate temperature of just 10 billion kelvins. And then you have different reactions. One is called deuterium-helium-3. Deuterium, hydrogen plus 1 neutron. Helium-3, 2 protons plus 1 neutron. That will be important later on. The deuterium-deuterium reaction happens at much higher temperatures, and actually our sun doesn't do any of these. It goes through a completely different cycle called the carbon cycle, and that happens even further off the scale. So that's quite good. Yes, I'm here. A rocket now is essentially a pressure vessel, which is good. We want a lot of pressure. We want high temperatures. Perfect. Let's poke a hole in the plasma to make a nozzle for our rocket. That seems to work. Of course, it doesn't work. I can't just take our everyday fusion reactor, which, by the way, of course, we totally have. I need to be a little bit more clever. One way to be clever is to use a special type of plasma confinement. Okay, a plasma is essentially a very, very good conductor. In fact, you can describe some metal properties if you describe the metal as plasma. Now, you take some plasma, in a cylinder usually, you establish a magnetic field, a homogeneous magnetic field in one direction. And then you very, very, very rapidly flip the magnetic field. What happens is the magnetic field can't penetrate all the way down to the core of the plasma. So you have your previously established magnetic field in one direction, and your now switched magnetic field in the other direction. So the magnetic field at the core is reversed from the magnetic field at the outside. That's why it's called the reversed field configuration. What you get through this configuration is this current. Your plasma is a conductor. You take the electrons in the plasma. You have a donut where the electrons flow, where your current flows. And as long as this current flows, the thing is stable. Of course, the plasma is not an absolutely perfect conductor, and this will shrink, slow down, and at some point your current is gone and the whole configuration isn't stable anymore. There is a problem with this thing, and that is that we do not have a complete mathematical model of how this works. At the very center, where the magnetic field is zero, all our calculations just break down. And right now, if you just do this once, you just have magnetic field, flip it, look how long it takes to be gone again. You can have it stable for about 1 millisecond. The nice thing is you now have a donut, and you can do stuff with this donut. You can throw it somewhere. You can accelerate it, other things. But first of all, we need this a little bit more stable. And the way to do this is to just apply a magnetic field around this donut in different time steps. It works like a motor, like a simple stepper motor. You just first have a magnetic field like this, then you do it like this, and so forth. And you just turn the current around in your donut. Problem, if you do it like that, if you do it like a motor, you're injecting another magnetic field, and that breaks away part of your confinement, and all the plasma escapes there. That doesn't work. But quite recently, the guys at Princeton University were clever again, and what they did, I hope you can see that here, yeah, they used 2 coils. And what these 2 coils do is they take one magnetic field, inject it, and immediately subtract it. So all they do now is they push this donut inside in one point, and they are now pushing this donut along all the time, and they are keeping this current stable. And they are currently at, I believe, 30 milliseconds stability. And they say, you know what? That's enough to get money from NASA. NASA gave them money to develop this bad boy. What they said, well, you know what? It's stable enough, we can do this. We will have our fusion plasma, and then around this plasma, we will drive another plasma, which will be heated by this fusion. And then, again, we drive the heat up, we have faster particles, we can go let them out faster, and now we have a very efficient rocket. At least in theory, this works. Because the other thing Princeton University did was they developed, as far as I know, the first computer model, the first simulation of how this confinement actually works. They didn't do a full computer simulation, but they figured out where exactly the zero magnetic field line is. Part of the reason why they got so much money from NASA. Then you see here they want to use deuterium and helium-3. The reason for that is if you have a fusion reaction, and you want a lot of energy from it, you have a lot of fusion reactions. If you take tritium and deuterium, you get a neutron. And the neutron has a lot of problems. First of all, it takes away most of your energy. About 1/5 of the energy of one fusion is taken away by the neutron. and the neutron will hit your wall and destroy your wall in certain places. If you take helium-3, you get a fusion and a proton. The proton still takes away about 1/5 of your energy, but it is now charged, and the charged particle will stay in your plasma, so it will heat your plasma, it won't hit your wall. That's great. That's why you can build this a lot lighter, because you don't need heavy neutron shields, which you would need in... Yes, we do have other fusion propulsion proposals as well. They did not get funded by NASA, most of them. So yeah, the main thing they did was they essentially took a current ion thruster and said, look, the biggest problem of these ion thrusters today is they need a very hot source of just heat to heat up the xenon they use and ionize it to make a plasma, and then they accelerate it. And we can use our fusion as this energy source. We can ionize this plasma or ionize it further because they need a pre-ionizer. And then afterwards, at the very end, you have this nozzle coil which actually does the acceleration. They claim to be able to start a 1 to 10 megawatt reactor in, yes, we heard it, 10 years. They proposed to go to Pluto with that, and they said, you know what, when it's there, we can shut the nozzle down, and then we have a 10 megawatt reactor, which will only weigh 10 tons, which is an amazingly great weight to power ratio. So if they are able to do that, I don't really care about going to space at 10 megawatts reactor for 10 tons. We could dig a hole here, have bit power this university and probably the rest of the city. Would be great in other ways as well. They proposed it as a rocket, because if you use a rocket, you don't need to be perfectly efficient. If you're not, you're still getting some energy you did not electrically invest into the plasma out in the back end, and that's already good. So there is another proposal, and NASA is actively developing this one. The problem of fusion is, how do you heat this up? How do you heat this up and keep it stable long enough for fusion to happen? And an idea here is to simply increase the magnetic field very, very, very rapidly, thereby increasing the pressure and temperature. Question is, how do you do that efficiently? This proposal says, you know what? We take some lithium rings. And if you have a conductive ring and you apply a magnetic field, you're propelling that ring. You can propel it inwards. So they're saying, again, we are starting with this plasma donut, this field reversed configuration donut. We're throwing it out the backside, and now we take 3 rings, and we apply a very strong magnetic field, and those 3 rings are now closing in. And they're closing in so fast, they're keeping their current that we just induced. And by doing that, the magnetic field is stronger and stronger at the inside, and at the very moment it hits the nozzle, it will all fuse, and then we can accelerate it backwards. Nice idea. The one they calculated would weigh 15 megatons, not tons, megatons, to produce 36 megawatts of power. Yes, it's usable, but as we've seen, the Princeton guys are much more, let's say, ambitious. Another problem is this thing is not a constant stream of particles to your backside. It's pulsed. They actually, you need time to refill these loops, these metal loops. And they say, you know what, we can do it with just 14 seconds in between, and between the actual rocket and our engine, we have just shock absorbers. That will work. Yes, it will work, no question about that. It's just that you now need to absorb the shock from a 15 megaton heavy engine to your rocket. So maybe there are other ways we can propel our rockets. Fission is another option. Again, we can take nuclear energy and maybe export some momentum from it. First of all, how does a nuclear reaction work? You take a neutron, you hit something you can split, some fissile material that will split, if you're lucky, and you get more neutrons. These neutrons you can now throw again at something you can split, some fissile material, you get a chain reaction. With every step, you get, yes, in this graphic, 3 more with each step, or the 3-fold of your previous step. You get an exponential curve, that whole thing blows up, and we can build nuclear bombs. we can write nuclear bombs. We did some active research on that. It is actually a very good idea, because nuclear bombs are something we understand quite well. In the 50s and 60s, we did a lot of research on how nuclear bombs would destroy or not destroy certain metal plates. And what looks very complicated here is just a mechanism to inject a neutron bomb through your pusher plate, as it's called. That's super simple. That's just mechanics. You just need a bunch of nuclear bombs, you throw them out your backside, you make them explode, you ride the shockwave. Simple. They calculated a lot of models, or actual rocket toy models, what they could do. They calculated you can go up to 3% of the speed of light with their biggest version. And somebody actually calculated if we start with that thing, we would just get 1 radiation death per year more. Great. If you built today a motor for a car that would result in just 1 more road death per year, you maybe get the Nobel Peace Prize. That's great. And with this thing, we can go to the stars. For other methods, we first need to talk a little bit about where these neutrons actually come from. I said you have you split one core, and then you get neutrons. That's not the full story. You do the splitting, you get some neutrons. In a nuclear reactor, you don't want all your neutrons to come from the fission itself. You get these 2 parts, which are extremely unstable. And when they decay, they release some neutrons as well. If you can use just the neutrons from the fission itself and have an exponential rate, you're what's called prompt critical. The prompt neutrons, which are there immediately, make you go critical. If you're only critical, if you only have enough mass that you still need these decay-produced neutrons, you're what's called delayed critical. That's what you need in a nuclear reactor to just be physically able to control this thing. If you just have a 10 to the minus 15th second to react to a change in your nuclear reactor, you've already blown up before your mechanics can start. If you've got 100th of a second, that's doable. That's not doable if you miss the point, but it's mechanically possible. If you don't have this delay, you have a nuclear bomb. Enter the nuclear dust drive. This is my favorite thing, especially because it pretty much matches what they use in the Expanse. You take, again, a magnetic field. You don't need the plasma this time. You just have charged particles of some fissile material. Uranium, whatever. Particles are very small, and that has 2 advantages. First of all, they radiate away a lot of heat. You're in a vacuum, so you can't conduct heat away. You need to radiate it. The higher a surface is, the more you can radiate away. So they're very easy to cool. The other advantage is, if you're having a fission, and there are these 2 products coming out, they're extremely fast. And through a thin piece of paper, they might get through. The thinner the paper, the easier they can get through. If you have extremely small particles, they can just escape the particle immediately. These particles are charged, these fission fragments. If you use a magnetic bottle, you can catch these charged particles and direct them in one direction outwards. This is actually an advanced version of this rocket engine. I'll get to the C part a bit later. You need a very heavy moderator around this confinement. I'll later explain what exactly the moderator does. But that's the biggest problem. This moderator is very heavy, and that drives down your ISP. Still, you could get an ISP of about 1 million seconds. And I didn't mention it because it's hard to calculate. With nuclear bombs, you get around 100,000 to 10,000 seconds ISP. You get 10,000 seconds from an ion drive, so that's good. That's extremely good. They calculated again that if you want to keep these spheres as solid uranium, and we're talking about pure uranium here, you can drive this reactor at about 26 gigawatts. If you're going even above that and allow your particles to melt, Then you can go up to 62 gigawatts. And then you would have a foggy plasma, and they say, nobody really knows how this handles, but it's possible. We could go to even 62 gigawatts with just dust, which is great. And then you get a power source for free. The C part here, you have several conductive rings. They're at different potentials. They slow down particles. When a particle slows down, it just hits a wall. They're charged particles. You reduce their energy. They hit a wall. You get current. Now you get, as electric power, voltage times current. So you just have an electric generator at the back here for free. That's great. I love this one. I really do. If we want to talk about actual reactors, we need to talk about this moderator thing. You have this fission, you get your neutrons, that's fine. And if you just have one fission, probably nothing will happen. Because you get neutrons at a certain energy, and those from the fission come out here at the very right end of the spectrum. Again, on the y-axis, we have some measure of reactivity. We don't really care about that. All we need to know is that we need to slow down neutrons so they actually react again and do some fission. Moderators come in many forms. One where we can use, for example, graphite, which we will see soon why we would do that. But we can also use water, which is used in reactors on the ground down here, hopefully. So, Project Pluto. Once they said, okay, we can't use nuclear bombs for tests anymore, we can't use nuclear bombs in space, what a bummer, they came up with this idea. It's a very simple design for a thing that would transport nuclear bombs from America to Russia below their detection level. They would actually call this the super low altitude missile. The idea was they're gonna drive at supersonic speeds. They would have a funnel in the front that would do the compression, and then they would have a nuclear reactor to heat the thing up. They built that shit. These are two types. There were actually three, but these are the two types they tested. The one on the left, the red one, that ran for about 3 seconds. They had something that would preheat and pressurize the air they would feed. And that one on the right side ran for 5 minutes. They actually had a full hangar they would fill with pressurized air, preheated, and then pump it through this reactor. There was a bit of a problem with the reactor. A classical reactor is extremely heavy because you have a lot of shielding. You have neutron shielding, you have radiation shielding, so they just didn't do that. That's a nice point about workplace safety here. They just left the radiation shielding away. That's why they couldn't fit a pilot in there. That program actually made huge contributions to automated flying. They had a fly-by-wire system, and if that crashes, they would just contour match the terrain, and then it would know where to fly and drop bombs. Yay. And they operated this reactor at just 150 degrees below the auto-ignition temperature of their base plate, which was, so they operated it to 2,300 degrees Celsius. Again, ambitious. If something happens, that's not just gone as in nuclear blast gone, that's gone and it burns up and you get nuclear radiating particles everywhere. What a fun time to be alive. Another idea was Project Rover. Project Rover was much more sane in some ways. They didn't use air, so you couldn't have anything auto-igniting. They used hydrogen. The idea was to take a simple reactor, a reactor type we know, pump liquid hydrogen through it. So you heat the liquid hydrogen up to very high temperatures. High temperatures means very fast exit speed. Fast exit speed means I have a very efficient rocket. So what you see here is one of the fuel elements. That's a 1.5 meter long fuel element with 19 holes in it. It was made out of graphite and then injected with uranium dioxide spheres. They would just stick to it and then coated in zirconium. Then you just have a reactor, your standard nuclear reactor. And here you see roughly the relation in size of the reactor itself to the nozzle, the actual nozzle. The nozzle is just about as big as your today rocket nozzle. You just have a bit of a feel of size here. They tested that. Here they did a lot of these reactors. The source I found actually claims this one is their last one, but I believe that it would have to be a lot bigger. I believe that's just a third version. The one you see tested on the left is the so-called Kiwi, because it's a flightless bird. They pump liquid hydrogen through this thing. So the fuel elements are about 22 Kelvin hot at the one end, and they're about at least 2000 Kelvin hot at the other end. There were some problems. Fuel elements broke all the time. They actually, at the end of this project, they said, we were flight ready now. We are only losing 17 kilo of fuel of reactor every 2 hours. They're just blowing out radioactive material there. At some point, somebody asked, what's the worst that could happen? Some stupid physicist answered, well, it could go prompt critical. Some stupid person said, let's try that. And they sent a reactor prompt critical. The tiny specks you see up there, that's liquid reactor. They just left that for 3 weeks because, well, it's highly radioactive. And then they sent in an army troop and said, you know what, you clean this up as a decontamination exercise. Everybody was very glad they at least did it. And that project, in the end, was shut down because they went to the moon and nobody wanted to go to Mars. Everybody was lazy. So they did something different. They were going to Project Timberwind. These elements had the problem, if you heat them too high at the one end and let them too cool at the other end, they break. Or you just flush them away with your hydrogen. Another idea was, we don't even use long elements, we use tiny pebbles. We use tiny 2 millimeter wide spheres. Fill them up with uranium, so the uranium in there can do nice things. It can go liquid, so this whole thing can be a lot hotter than our previous elements, or our previous fuel elements. And then we can heat up our hydrogen again. So both are the best pictures I've found. This, of course, was a secret mission because the military did it. I'll get to why. What you see here, I just wanted to show you how this all would have looked in the end. You just let in liquid hydrogen at the top. It would come out the bottom. And here you have a more functional diagram. You may have noticed there are no control rods in this reactor. You don't use control rods. What you do is you have, at the outside, a very well-cooled control cylinder that has a neutron catching material on the one side and a moderator on the other side. So if you turn the cylinder, you either get the moderator, which slows down your neutrons, or your neutron catching material, which takes away your neutrons. There is a nice line that they actually, they made it fail-safe. Fail-safe in this case means even if one of the control rods is stuck, you can still get it supercritical. So your engine won't fail. Any questions to these drawings? Because I know they're quite complex. Wonderful. So the great thing about this thing is it actually managed an ISP of 1,000. Oh, I should have mentioned the Project Rover before managed an ISP of about 800. And they actually at once built a reactor, the last reactor they built, drove at 4 gigawatts, which at the time was the strongest reactor ever built. So the reason it's on this list is what they wanted to use it for. They wanted to use this engine to intercept missiles. If you intercept a missile with something that has a nuclear reactor, the whole thing goes boom. And you're distributing your nuclear reactor everywhere. Have fun with that. But something good came out of that. They invented a new neutron shielding, or called bath, and the salts are probably what they took at the time. So for the next reactor, we need to talk a little bit about how a moderator actually works. You have your fast neutron, and you can interact with other nuclear cores, with other nuclei. If you have a very heavy nuclei, your hydrogen comes along, hits it, and is essentially reflected. No energy is lost. On the other hand, if you take a very light nuclei, your neutron comes along, hits it, and you play billiard. Neutron stays, other thing goes faster. A lot faster, actually. This means that your moderator essentially takes away the kinetic energy of the neutron. You heat the moderator by the neutron getting slower. Hydrogen, again, is an ideal moderator because it's essentially the nuclei of the hydrogen is essentially the same weight as your neutron. You can use other materials that are light as well, but hydrogen works best. This is a very recent concept. I believe it's from 2016. The idea here is to create an immense flow of fast neutrons. These fast neutrons heat your hydrogen, then you get your extremely hot hydrogen without having heated the fuel. Great. First problem, you need to drive this thing prompt critical. Very, very, very quickly. Then you need to drive it subcritical again. Very, very, very quickly. And I told you that you have these fissile products which will give you delayed neutrons. You need to get them away. So you cool this thing with liquid lithium. Liquid lithium takes away your fissile your fission fragments. I've talked about very fast. They're saying you want to do this at around 10 kilohertz. 10 kilohertz, reactor up, reactor down, reactor up, reactor down. I told you about the Project Rover having problems with their fuel elements being essentially eroded away by the strong heat differences on the fuel element. The paper did not go into detail how they want to avoid that. They said from a thermodynamic spectrum, from how fast heat is conducted through our uranium fuel, through our lithium, through our hydrogen, this works. The upside, this thing is just, you see it here? 40 centimeters by 40 centimeters by 1 meter tall. This is just about a cubic meter in size. And you can get, I forgot to write it down, a lot of power from this. You, in theory, can get an ISP in the ranges, again, of the 1000s or more. As you can see here, these red lines, these are your fuel, uranium carbide. You have on the one side hydrogen, on the other side you have lithium, immediately side by side. We were talking about eroding away reactor and that's a problem. If you erode away this reactor, you have big problems. Another problem is that although this thing can put out a lot of power, 95% of your power is not going to your hydrogen, because 95% of the power is actually going into the fission fragments, which are carried away by the lithium. That's also why you need to cool the lithium again. But again, if we can build this, I want to dig it in my cellar, and I have a very, very strong reactor which can power a city. Nice. Since we're always having problems with our reactor melting or eroding away, let's just vaporize it. The idea here is that we take our uranium, we slowly feed it through the back, the uranium immediately boils off in a gas bubble. We keep this gas bubble off the walls by just pumping through hydrogen at a very, very high rate with a lot of pressure. And we have some bypassing hydrogen in order not to lose the whole uranium at the same time. The Reactor Concept wants to keep the uranium inside this reactor as long as possible while heating up the hydrogen as quickly as possible. This is from a simulation they did. No, we didn't build that, thankfully. But they simulated this, and I'm going to talk about how realistic it is in a bit. First of all, the concept itself. This is just a much nicer picture. What you can see here is that the gas is supposed to be about 55 Kelvin hot. I've seen different numbers in the 60,000s and so on. The problem you have, hydrogen has a bond energy that is pretty much going away at around 52 Kelvin. When you do that, you have a hard ultraviolet light source. There are actually concepts called the nuclear light bulb, but I'm not going to talk about them. This ultraviolet light source immediately splits your hydrogen. And I didn't find any research on what exactly happens. What I think happens is you have your two hydrogen atoms, which immediately rush away the hydrogen surface of your liquid hydrogen, essentially just blow out your nuclear reactor through the back, and you're left without any power at all. The fuel we keep inside, because we're just pumping through all the time, has about 2 minutes to react. Different people say different things, but we are at about at the maximum 10% usage of our nuclear fuel, which is more than the 5% we used in the previous example, but still. The problem we have here is that we would need to be able to pump our hydrogen at around 1,000 bar. This may be possible with liquid hydrogen. With gaseous hydrogen, we're pretty much technically leveled out at around 700 bar. Maybe there's been some development, but that was the last time I checked with a material physicist. So we are pumping out our nuclear reactor to the back anyway, so why not have that as a concept? This is the nuclear saltwater rocket. Nuclear saltwater rocket works in a very simple way. You have your uranium salt, you dissolve it in water, then you take a volume which is supercritical at that volume. First of all, that creates a problem if you want to store this liquid, this nuclear salt water. You need to store it in very, very thin tubes, which are laced with boron, so they the tubes themselves catch away the neutrons. The upside is this thing just starts from itself. You always have something that will decay and release a neutron. So if you just take supercritical amount of this water, it will just go boom. Nice. Problem, we can't really find a material in which we can build a tube that would withstand a nuclear blast. Solution? Well, we said these neutrons are popping into existence at an exponential rate. So if we just rush our water through this tube, we can create a tiny bit of neutrons, create more and more and more and more and more, and have the wave that will actually start our prompt critical reaction just outside the tube. And that can withstand a nuclear blast. I brought a model here of a nuclear saltwater rocket. This tiny little tube can give you 13 meganewtons of thrust. All you have to do is pump through water. You can build that in your backyard. That's why I love it. Just for comparison, our most efficient rocket engines, the Space Shuttle main engine, loses a tiny bit to this concept, which is essentially riding a nuclear blast constantly. We don't need any moderators, we don't need any mechanics. The tiny problem, we cannot shut it down without going boom. Because if we shut it down, the neutrons will just rush through and our tube goes boom. We cannot start it without going boom, because if we rush through water, we don't know when the first reaction will happen. So you rush through a lot of water, and then at some point, there's a lot of water that can go boom at the same time. Apart from that, we need to pressurize the water to around 11,000 bar. But if these tiny problems are solved, and I strongly believe they are solvable, I hope so, because it would be awesome, then we could accelerate away from our solar system at a rate of around 3G for 10 years to go wherever we want. And with this, I am closing. I hope you all started to believe in writing a nuclear bomb. Thank you. I'm available for questions. Here are my sources. This will, of course, all be uploaded, and you can look up where I found all these funny pictures. Thanks to Zoe over here, who actually drew the pulsed nuclear rocket. No questions. I mean, it's questionable in and of itself.
One of your first engines also produced electricity. I think it was the third one, or
this one.
something like this. How would you get rid of this electricity if you don't need it in your space shuttle?
You could just turn off the... Okay, the way you do it is you have charged particles coming out at a very high speed. You're taking essentially two condenser plates, and you're applying a voltage, and this slows the particle down, and then it will hit the wall. If you just turn off this voltage, it will just radiate off into wherever. You can take some magnets to drive them away from your rocket.
Has this one been tried, actually?
This one was not tried. It's a quite new concept. I believe it was 2005. Yes? Where things around this was published. But what was proposed was to build a reactor like that. Because a big advantage is that since this thing is prompt critical, you're throwing away all your delayed neutrons, you're having a quite high neutron flux, and so you could just throw in some unburned or wasted fuel and reburn it inside this reactor. I would not recommend it.
Sorry, this is the only drive that I didn't understand at all. Could you explain it again, how it works?
Yes.
Very simply?
You have your dust particle. Somewhere inside this particle, a nuclear reaction happens with a lot of energy. You have your two fission fragments, which will leave it in both directions. Your particle is so small that there is the chance like 99.999% that those particles will leave your fuel grain. Then they're inside a magnetic field. The magnetic field drives them to one of the two ends. At these ends, they can just leave your reactor. And since 95% of your energy is within these in the kinetic energy of these fission fragments, you can utilize your fuel to a very high percentage. How is it? The direction happens with the magnetic field. This is essentially, again, you're having something like, where is it? You're having something like magnetic confinement for a plasma. For these charged particles, it just works the same way. If you just have two very strong magnets with a weaker magnetic field at the center, that's just, I would need to go into plasma physics why. But then you can hold your particles in here, and they will only leave through one of the two endpoints, if your magnetic field is strong enough.
Which one do you think is the most reasonable?
Question is what you want. If you're asking me which one could fly in 50 years, nuclear bombs, definitely, without a question. If you're asking me which one would I like to see flying, nuclear saltwater reactor, definitely. There is actually a line in the paper where he states, because there are some, you can't ignite nuclear bombs in the stratosphere, he writes, clearly this is not a nuclear bomb. And I think the simple fact that you have to state that outright tells you something about the system. A prominent web page, I can't recall its name, actually stated simply writing the environmental impact factor for a test would pose an interesting challenge, because you're just blasting off radiative material in all directions. And if you're asking me which one do I think will most probably fly, I actually believe in the Princeton University guys. They found something in very recent past that wasn't known before. They are working very hard on it. They got the NASA grant, so at least they think it could work. It's ambitious, but that seems plausible. And the dust drive I just love, because if you read The Expanse, just the lingo they use, it pretty much fits this drive. Sorry. This drive. Yes, that's all. Thank you. Thank you for your attention.